Okay, thank you very much. And I'm actually going to start by just reviewing some things from last time to motivate the conjectures I want to talk about for p-adic L functions. I want to review the Archimedean setting. So let's consider a Dirichlet character, just a homomorphism from z mod nz star q bar star. And I'm going to assume that it's even, so chi of minus 1 is 1. And I'm going to always fix an embedding of q bar into the complex number, so I can view this as a complex valued character as well. And it has associated L function, which is just the usual Dirichlet L function. Just chi of n over n to the s, and you can sum over the n that are relatively prime to capital N. So this converges for real part of s greater than 0, in fact, not just 1, if chi is not the trivial character. Okay, and I just want to keep a running example. Chi 5, sort of really non-trivial character of conductor 5 that is even. So this is a character to plus or minus 1. This is just a quadratic character. So this would be, well, chi 5 of plus minus 1, I said, has to be 1. And then if I want it to be non-trivial, then I'll take the remaining class, which is plus or minus 2. I'll define that to be minus 1. Okay, and so then the L function of this thing, okay, is just 1 minus 1 over 2 to the s minus 1 over 3 to the s plus 1 over 6 to the s minus 1 over 7 to the s dot 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 dot. Oh wait, did I do that? I did something wrong. No, that's right. Okay. So you keep going. So in each group of 4 terms in a row, there will be 2 pluses and 2 minuses. Okay. And then I defined circular unit, or cyclotomic unit in this case, which for the general case, you define it to be, you take the associated cyclotomic units that we've been seeing in Sharifi's talk, and you take the... Oh yeah, what happened to 4? See, it's very hard to do explicit examples. It's much better to work in generality. Plus 1 over 6 to the s. Yeah, okay, minus. I could tell there's something wrong when I wrote it down, but I couldn't figure out what it was, so that's good. Okay. Okay, thanks. So this lies in the chi inverse component of the unit group. Tensors. Again, this is not necessarily a unit in general. If n is a prime power, but you could sort of just divide out by something constant to make it a unit. 1 minus zeta n, and then sort of makes the same number if chi is non-trivial. Okay, so all right. So just as an example, in my example for this chi 5, this is just 1 minus zeta 5 times 1 minus zeta 5 inverse over 1 minus zeta 5 squared times 1 minus zeta 5 to the minus 2. And so you don't need any of this tensor C nonsense when chi takes values in plus or minus 1. It makes sense to raise a number to a plus or minus 1 power even without tensoring. So this is actually an honest unit, and you get 3 minus root 5 over 2. K star. So K in general will be Q adjoin zeta n. Okay. In fact, as I described last time, it'll be if chi is even, this will be in the subfield fixed by complex conjugation, the totally real subfield of this. Okay. So then I discussed a theorem of Dirichlet, sort of analytic class number formula, that gave the value of the derivative of this L series at 0 in terms of this circular unit. Okay, so the theorem of Dirichlet is at L prime of chi at 0, which, by the way, I mentioned there was a functional equation, but I'm not sure if in this particular case I said what the factor would be, which relates to the value at 1 of chi inverse. There's a little factor, this Gauss sum, which can be viewed as a simple case of these epsilon factors that Mahesh is talking about. And that this, so the theorem is not this is just the functional equation. The theorem is that these common values are equal to negative 1/2 log of u chi. And this is actually the calculation we did using sort of the Hurwitz-Zeta function. So yeah. No, go ahead.
Can I ask a question about u chi? So if you divide by this 1 minus zeta n, I mean, usually that's not going to contribute anything, right?
Yeah.
Because of the tensor by chi. But if it does contribute something, then it won't lie in the eigenspace, will it?
Say that again. If it contributes.
Right. I mean, if say the character is trivial, then it's not.
Yeah, but chi is not trivial.
Okay.
That's how I started. That's why I wanted to take a non-trivial character.
Oh, okay. So
Yeah,
it's just equal.
It's just equal to the same thing, but I just wrote it this way so that it's a unit. Because I said it's an OK star. Yeah, that's what I'm just writing it so that, yeah, so, yeah, I don't want to, if chi is trivial, then I'm not taking this. Yeah. Okay. Okay. So, right, so what was I saying? Oh, yeah, so just as an example, L prime of chi 5, 0 is root 5 over 2. That's the Gauss sum is just root 5 in this case, times L of 1 chi, L of, I've been writing my chi's first. So chi 5 inverse is chi 5 again. It's a quadratic character. And this is negative 1/2 times the log of this number 3 minus root 5 over 2. Okay? So, yeah, so this is actually something you can calculate on a calculator. This is, I'm worried about trying to write it down again if I'm making a mistake. Okay, 1 minus 1/2 minus 1/3 plus 1/4 plus 1/6 minus 7. You can just do this sum, go out pretty far, and then calculate this on the calculator. You'll get the same number. And I did that to check that these formulas are actually accurate. Okay, so that's just a little review, a few minutes of review from last time. And now I want to talk about p-adic L functions and some analogs of these formulas that I've been writing down. Okay, so maybe I should say ... so we know it's a series. Okay, so the simplest example of a p-adic L function is the Kubota-Leopold L function. Okay, so I want to fix an embedding, just like I fixed an embedding of q bar into C, I want to fix an embedding of q bar into CP, which is the completion of an algebraic closure of QP. Okay, and the theorem of Kubota and Leopold is that there exists a unique p-adic analytic function so here I'm retaining the assumption that chi is even, but I'm not, and the function I'm going to write down is actually going to be analytic if chi is non-trivial, and if chi is trivial, it'll be analytic except for a simple pole at s equals 1. Okay, so with saying that caveat verbally, I'll just write the statement that that p-adic L function is a map from ZP to CP, the following interpolation property, that the value of this function, if I evaluate it at an integer, a non-negative integer, okay, then the value will be some Euler factor that I'll write down in a moment, times the value of the classical L function, but you have to twist by a power of the Teichmuller. So you change which function you're looking at based on what n is mod p minus 1. Okay, so this is for all integers n greater than or equal to 1. So the arguments are non-positive integers. I think I may have said non-negative a second ago. I mean non-positive integers. Okay, so so let me put in the Euler factor here. So it's exactly just the Euler factor of this L function at the prime p. Chi omega to the minus n of p. P then minus 1. Okay. So, and again, where omega is the same omega that has appeared in other talks, it's the Teichmuller character. Which, if we want to think as a Dirichlet character in our setting, will just be mapped from Z mod PZ star to P minus first roots of unity in Q bar star. This is the Teichmuller character. Okay, so if n is congruent to 0 mod P minus 1, then this just doesn't appear. Okay. And these integers are dense in ZP, so if the uniqueness is obvious from just the continuity and the interpolation formula if it exists. You have to show, however, that it exists. And one can prove this essentially by using the Kummer congruences that Romiar stated earlier today, or at least he stated the first Kummer congruence, and then there's higher Kummer congruences. And those basically imply this result. Okay, so now the first special value formula that I want to state is an analog of this result of Dirichlet, which is a formula for Leopold for the value of this p-adic L function, this Leopold p-adic L function, at the point s equals 1. You see, s equals 1 is not included in this interpolation formula because if n is greater than or equal to 1, 1 minus n is less than or equal to 0. Okay, but yet the value at 1 is determined by this interpolation formula because there are plenty of negative integers whose p-adic limit is equal to 1. So it has a certain value. And the theorem of Leopold is that the value of this p-adic L function, and I'll write it in terms of chi inverse rather than chi, just to the yoga I've been using throughout these lectures is that we're looking at the L function of a character chi at 0, and we'll look at that's related via the functional equation to L of chi inverse at 1. So just to be consistent with that, I'll look at the value at LP of chi inverse at 1. Okay, and this is equal to negative 1 over tau of chi times 1 minus chi inverse of p over p. Jesus, horrible. I don't want to squeeze the formula. Let me write it here. It's equal to negative 1 over tau of chi. So I'm basically writing the exact same formula as the formula for Dirichlet's theorem. Okay, except I'm going to replace the classical logarithm with the p-adic logarithm. Okay, so if I go back, hopefully that's the exact same formula, that I wrote down for the value of the classical L value at 1 is L of chi inverse of 1, which is negative 1 over tau of chi times the log of u chi. So you would expect this kind of interpolation factor because that's the thing that shows up here. So this would be sort of, if this was in the range of interpolation, that's what the interpolation form property would be. And okay, so that's that's Leopold's theorem. So okay, so I should say where log p is, where log p OK star. So you can think of OK star as sitting inside CP star, and then you apply the p-adic logarithm. Okay, is the p-adic logarithm. And you can extend it by linearity over q bar to a map on u chi. So this makes sense. Okay. So now, okay, so that's the formula. So for example, for this chi5 that I wrote down, you could say, well, if p is 3, then L3 of chi5 at 1 is negative 1 over root 5 times 4/3. I guess it comes from this factor. Why do I have 4/3? Yeah, I guess. Okay. Is it 2/3? Somebody can check for me what the. Somebody can check for me if that constant is right. And then log 3 of 3 minus root 5 over 2. And it works even if your p divides the conductor of your character. So if I took L5, the 5-adic L function for this character chi5, then you get minus 1 over root 5. Okay, and then this chi of p goes away. Okay, this is just 0, and you get log 5 of the same unit. Okay. Okay, I think it's right. Okay, good. That's what I have in my notes. All right, so now the question is, but what about the formula at 0? So this is the formula at s equals 1, which is analogous to Dirichlet's theorem. It's just replacing the classical logarithm with the p-adic logarithm when you replace the classical L function with the p-adic L function. And the important thing to note is that it's not equivalent. That is, we can't simply say what the value at 0 is from the value at 1 because there's no functional equation for the p-adic L function. So let me just say that LP of chi s does not satisfy a functional equation. Relating values at s equals 0 and s equals 1. Okay, there's no functional equation relating the values at s and 1 minus s. So, but the value at s at 0 is even simpler than the value at 1 because it's in the range of interpolation. Okay, so that's actually an easier question to answer. That is, if I take n equals 1 in my interpolation formula and you plug it in, then what you get is that L of p of chi 0 is nothing but 1 minus chi omega inverse of p times L of chi omega inverse 0. And as Romeo explained today earlier, this is, we have an explicit formula for in terms of these generalized Bernoulli numbers. This is minus b chi inverse chi omega inverse comma 1. This is a Bernoulli number. So we have an explicit formula for this. It's an explicit algebraic number. Okay? Okay, but that's not the end of the story for the value at 0. And the reason that it's not the end of the story is that it's possible for that Euler factor to vanish. Okay, that 1 minus chi omega inverse of p. In which case we have the value 0 for the value LP of chi 0, and then we want to know what the value of the derivative is. Okay, so that's something that happens based on what setting you're in. And so from this perspective, with the trivial 0, it makes sense to think of this as an odd character now, which we'll call psi. Okay, so this is just a renaming of variables. So call chi omega inverse, call it psi. Okay. Well, I'll just say maybe equals psi. Okay, and so now let's start over just from the perspective of psi. So now let psi be a character from z mod n z star. Okay, so this is not necessarily the same n, as I'll explain in a second, q bar star, such that psi of minus 1 now is going to be equal to minus 1, because omega of minus 1 is minus 1 and chi was even. Okay, so the point is that if chi has conductor n and this omega has conductor p, then if n and p are relatively prime, then this will have conductor np. Okay, but if chi is conductor n and omega has conductor p, then chi omega inverse could have conductor n, or it could have conductor n over p, which could now be relatively prime to p. And so that's what I might be calling my new n here. Okay, and that's exactly the setting that I want to consider. So suppose we're in a setting where that p does not divide n, and in fact that psi of p is equal to 1. Okay, so then this LP of, well, chi is just psi omega at 0 is equal to 1 minus psi of p times L of psi at 0. Okay, so now this is just 0, or I shouldn't put an x through it. I should just say that it's equal to 0. Okay, and this is the so-called trivial zero phenomenon that I'm referring to in the title of my talk. Okay, because it's 0 not because the interesting part of the interpolation formula is 0, not the thing that you're interpolating is 0, but rather the Euler factor that you had to throw in to achieve p-adic continuity, that is 0. So that's why it's called a trivial 0. Some people also call it an exceptional 0. Okay. Now, when you have an L function that's 0, you should ask, what's the value of the derivative? Okay, so this was studied by Ferrero and Greenberg, and they related the value of the derivative of the Kubota-Leopold p-adic L function at 0 to special values of the p-adic gamma function. And then, using work of Katz, Gross and Koblitz were able to relate those special values of the p-adic gamma function to p-adic logarithm of a certain Gauss sum. So let me state that result all together in one theorem. So this is the theorem of Ferrero-Greenberg. Katz and Gross and Koblitz. Okay, so I'm stating it all together in one theorem, and I won't even actually mention the formula for the Gauss sum precisely. I'll just state that it's a Gauss sum, which is that the derivative of this p-adic L function, okay, if you normalize it by the classical value of the L function, which again is just some Bernoulli number, this is negative b psi at 1, okay, that this, but I'll just write it as the L function to be more suggestive. Okay, so divide out by this simple algebraic number, which is non-zero, that this can be written in terms of a unit as the p-adic logarithm of a certain unit in a space that I'll write down in a moment. And I'll write it in kind of a suggestive way as the p-adic logarithm divided by the p-adic valuation of a certain unit, v psi. So v is, for v psi is actually a p unit. Okay, and again I'll tensor up, so in this case with CP, so that I can look at the chi, or the psi inverse component of this group of units. Okay, and this turns out to be a one-dimensional vector space. Okay, by the Dirichlet unit theorem. So it's one-dimensional over CP. So it makes sense to take any non-zero element that's a basis for the one-dimensional vector space. Then I could take two homomorphisms on that one-dimensional vector space, the p-adic logarithm and the p-adic valuation. And the ratio gives you the value of the ratio between the derivative of the p-adic L function and the classical L function. So, and I'll just say that v psi can be given explicitly as a certain Gauss sum. In fact, if you normalize it correctly, then you can write down the Gauss sum explicitly in such a way that its p-adic valuation is the classical L value, that's Stickelberger's theorem, and then the p-adic logarithm is the negative of the derivative of the p-adic L function. Okay, so somehow you can normalize this. You can write this in an explicit way such that this matches up with this, and this matches up with this. Numerators match up and the denominators match up. But in the spirit of writing things just rationally instead of integrally, as I did yesterday with Stark's conjecture, I'm just going to say, well, let's take any element of this vector space, and I want to write something that doesn't depend on the choice. Then I take this ratio. So if I multiply this by a scalar, then these are linear homomorphisms. That scalar would cancel. This is independent of the v psi that I choose. That's non-zero. Okay. So now I want to talk about generalizations of this to an arbitrary number, totally real number field, as I did with Stark's conjecture, generalizing from the calculation we did explicitly with circular units, and then generalizing to Stark's conjecture for the general totally real field, or general number field case, I should say. Now I want to generalize this to a general totally real field, okay, which is the setting in which we have p-adic L functions. So now let F be a totally real field. Okay, which is, in the notation of my first talk, means that R2 is 0, that all the embeddings of F land into R. There are no embeddings into C that don't land in R. Okay, and now let K over F be an abelian extension. Okay, and K, let's say that K is totally real as well. And let's let chi be a character of this Galois group. Okay, so this is a character to some, say, number field E, so it goes into E star, and as usual it takes E embeddings into C and into CP. Well, I guess I can just think of E being inside of Q bar, and so I've fixed already embeddings of Q bar into C and CP. So I can think of this character as C and CP valued. Okay. Then we have the L function that I defined last time, okay, which is the sum over all ideals, okay, that are relatively prime to the conductor of the character. Okay, of chi of sigma A over the norm of A to the S. Okay, with real part of S greater than 1. Again, just in the other case, if chi is non-trivial, then you can take real part of S greater than 0. Then Deligne and Rivet, along with Casounogas and Barsky independently, the three independent proofs, prove the existence of a p-adic L function analogous to the Capote-Leopold L function that interpolated the special values of this L function. So this is a theorem. Deligne and Rivet, Perret, Casounogas, and Daniel Barsky prove that there exists, so this is just a generalization of the Capote-Leopold theorem, there exists a unique p-adic analytic. And again, it's only analytic if chi is non-trivial. If chi is trivial, there may be a simple pole at S equals 1. LP of chi S from ZP to CP. Okay, such that it satisfies the exact same interpolation property as before. So LP of chi at 1 minus n, and now I need to take out the Euler factors at all primes dividing p. Be 1 minus chi omega minus n of p times the norm of p to n minus 1. Okay, times the value of the classical L function at 1 minus n. Right, so to make sense of this, maybe I should have said this in the Capote-Leopold case. For this even to make sense, both sides have to be algebraic, so that, I mean, this is a complex number and this is a number in CP. How can they be equal? It makes sense if they actually both lie in Q bar, so then we can ask for them to be equal under these embeddings. Okay, this is a theorem of Klingen and Siegel, and also of Shintani, that independently that these are algebraic numbers. So that makes sense. Okay, so again, this is for all n greater than or equal to 1 in Z. Okay, and now I can state some conjectures. They're only conjectural in the case of a totally real field for the analogs of the theorems that I wrote down, that of Leopold at s equals 1, and that of Freire, Greenberg, Katz, and Gross-Koblitz at s equals 0. And so those are the so-called p-adic Stark conjectures due to Serre and Gross. And I should mention I should mention that sometimes when you hear about the p-adic Stark conjectures, I mean these are global units, and we're taking p-adic logarithms, but they're global units. So it's still, and they're essentially the same units that are showing up in the classical Stark conjecture. It's just giving a p-adic formula for them instead of a classical formula. So the conjecture, so Serre's conjecture, well, one of Serre's many conjectures, Serre's conjecture regarding the p-adic L function is that the value at 1 is given exactly as a formula, such as Leopold's conjecture, and I'll write it, and just as I did with Stark's conjecture, in kind of a rational way, which leaves some ambiguity, but I'll write it as a regulator times an ambiguous constant that I'll write as C chi. Okay, so where C chi P is an E star. Okay, and R chi P is a p-adic regulator. So in the one-dimensional case, it's just a p-adic logarithm, but in the higher dimensional case, it'll be a determinant of such things. Okay, so I'll just say the group that I called U chi. So this is OK star. So now I think when I originally wrote down U chi earlier, I was writing it over this tensor over C or CP, but it's better now to just take this this field E where chi lands so that my ambiguity is small. It's just living in this number field. Okay, so this would be defined up to some element in E star, and so that's why I need this ambiguity anyways as I've written it. So this is exactly the analog of Stark's conjecture that I wrote down last time, stated at 1, where I have p-adic things instead of classical things. And in fact, there was some question about how precise can you make them. Well, I didn't answer that very precisely last time, but one thing I can say is that you can compare the two, and basically the C chi's should cancel if you take the same basis to make the R chi's. Right? So the C chi should basically be the same. C chi P and the C chi, if you take the same basis to be the for the R chi P and the R chi. So that makes the theorem very precise then. If you divide by the classical one, then, well, you can't really divide a p-adic formula. Okay, let me strike that last sentence. But basically that makes this statement very precise relative to the classical one. There might be some Euler factors, but essentially the C chi P should be the same as the C chi if you choose the same basis for the regulators. Okay, so I'll just say that. So recall that Stark's conjecture was that the leading term of this chi at 0 is equal to C chi times R chi. And again, this is related to the value of L of chi inverse at 1. Right? So there's some factors that show up in the functional equation, but if you take the same basis to make R chi and R chi P, then the C chi should essentially be the same, up to some explicit constancy you need to write down. Okay, so that's the analog of Leopold's conjecture, Leopold's theorem, I should say. And now what I want to state is the analog of the Ferrero-Greenberg Gross-Koblitz theorem, which is the trivial zero phenomenon, and what then I'm going to shift my focus to as we move forward. Okay, so now I want to take a different setting, which is we write as before, we replace chi omega inverse. We replace that by psi. Okay, so now psi is a totally odd character. And so I look at the fixed field of psi and call that k. So that'll now be a totally complex field. Okay, then let's see. Okay, and then I let my r chi, r psi. So this is going to be the order of vanishing. This is going to be the number of primes p of f above rational p such that psi is equal to 1. So this is equal to the number of those terms in the Euler factor, that p that I removed in the interpolation property, that were 0. It's the number of terms that are 0. And so then the conjecture is, Gross's conjecture, the first part, is that that's the order of vanishing of the p-adic L function. But before I say that, one thing you can prove is that the algebraic counterpart, that is the group that I wrote down before in this case over Q, there's no difference in this case. Sorry, star. Okay, that if you look at the psi inverse component, then it's a theorem. Okay, so this is known that the dimension of this as an E-vector space is exactly equal to R psi. Okay, so so that's the algebraic. So there's always these formulas are an interplay between an algebraic side and an analytic side. So the algebraic side, at least we know the right dimension, and that's just the Dirichlet unit theorem, the Galois equivariant version of the Dirichlet unit theorem. So now the conjecture will be that the analytic side is given by the regulator applied to the algebraic side. So the conjecture of Gross the first is that the order of vanishing of this p-adic L function at s equals 0, the associated p-adic L function, is equal to R psi. Okay, and then the second is that the leading term is again given by the same form, a regulator times an error term in E, excuse me. So this C psi p is just some fudge factor, and R psi p is a p-adic regulator of this group V psi. Okay. So let me say in words some things that are known. So first of all, when R psi is equal to 0, then this is clear just from the interpolation property. And if R psi is greater than 1, right, so R psi equals 0 is trivial by interpolation. And R psi is greater than or equal to 1 implies that the order of vanishing p psi omega is greater than or equal to 1, again by the interpolation. Okay, and some other things that I'll say, and I'll say them again in my slides, so maybe I don't need to write them down, but the fact that this side is greater than or equal to this side is a theorem due to Wiles by his proof of the main conjecture, and sort of new proofs have appeared recently by Spies and also by myself and Charlevoix that look only at the p-adic L function rather than the main conjecture, which is a little bit more involved. Okay, so let me move to the slides now. Okay. All right. Okay, so first I'm going to take a few minutes just to summarize everything that I've said so far. So for Dirichlet characters, if we have a Dirichlet character, I wanted to mention something. These slides are on my webpage, so if somebody has their computer here, they can kind of look on your iPad as the slides on your own as you're going along. So just if you Google my name, then you'll find my webpage, and the first link on my webpage is the slide of this talk. Okay, so you have this Dirichlet L function associated to a Dirichlet character, and you have the associated group of units. So the special value formula, I just wanted to put it in a table. So the values for an even character, so these are so-called critical values. I haven't defined that in my lecture so far. I will next time. But basically, these are the values that you can kind of interpolate to make a p-adic L function. So they're values that if you divide out by the appropriate period, should be algebraic. In this case, there is no period you have to divide out by. They're just algebraic on their own, at least at 0. And then there's a period that arises from the functional equation at 1. So here's the special value formula for an odd character. I think I said even. For an odd character where chi of -1 is -1. Okay, so the values there are critical. Then for an even character, they're non-critical, and you get that's when you get regulators showing up. So you have the circular unit, and you have Dirichlet's unit theorem, which I explained, and we actually calculated using the special value of the Hurwitz zeta function last time. And if you rephrase it at 1 via the functional equation, then you get this equation. Okay, so now I want to talk about the p-adic analogs, summarizing. So again, for p-adic L function, and on the one hand, it seems like you have half as many things to consider because you only have ones associated to an even character. On the other hand, you have 2 points to consider now, 0 and 1, because there's no functional equation. So you then, again, have sort of the same number of formula in the end. So the special value formula for an even character at 1, that was Leopold's theorem, which is I didn't want to bog down the slide with the precise constant, so I just put a star. But it's essentially given by the p-adic logarithm of the same thing whose classical logarithm gives you the classical L function. And then if you look at the value at 0, as I explained, that's just something you can write down by the interpolation property. It's just some Euler factor times the classical L value. Now what becomes interesting is if that Euler factor vanishes, and then it's better to look at from the perspective of the odd character chi omega inverse, and you say, and that will vanish, so when psi of p is 1, then 1 minus psi of p is 0, so then this becomes 0, and that's called a trivial 0. And then we get that the derivative of the p-adic L function is the p-adic logarithm of a certain p unit now, which can be written explicitly as a Gauss sum. And this is the theorem of Gross and Koblitz. Okay. Now we look to the p-adic Stark's conjecture, the higher dimensional cases, and the p-adic analogs for both. So the Stark's conjecture at 0 and 1, these are equivalent by the functional equation. Okay, and so it's the r-kith derivative at 0, the leading term there, and the value at 1. And these are the known orders of vanishing here. Okay, and you have the regulator of the group of the chi inverse component of the group of units. Okay, and that's Stark's conjecture. And then in the p-adic setting, there are 2 different conjectures based on whether you're looking at 0 or 1. Okay. So from the perspective of an even character, looking at the value at 1, you get the generalization of Leopold's theorem, or the p-adic analog of this conjecture. So this is just sort of, or I guess since it's at 1, it's just to this. It's just the exact analog, where you have a p-adic regulator instead of a classical regulator. And then the value at 0, or the leading term at 0, is the Gross-Stark conjecture. So the value at 0, again, is just given by interpolation. And the number of Euler factors that vanish is exactly this r psi. That's the definition of r psi. Then you expect, and it's not by any means obvious, that there will be a 0 of that order. Okay, so even though there's r terms that are r psi terms that you're multiplying together that are 0 in the interpolation, that doesn't mean that the p-adic L function has to have that kind of order, because those factors aren't all p-adic analytic functions that you're multiplying together. Okay. All right, and so this is the Gross-Stark conjecture. All right, so I put it all together on one slide. Oh, I didn't do that. Okay. So let me say what's known about Stark's conjectures. So I ended my talk last time with this, the Dirichlet class number formula, when chi is the trivial character for any number field. Okay, the leading term at s equals 0, the Dedekind zeta function is known. Okay, it's a Dirichlet class number formula. When chi is quadratic, we can deduce it by factorizing. Okay. So by the way, I should mention something. Why is this case known, chi is 1 known, but not the general case known? And as Cruz explained to me once, the reason is that when you have an L series or a Dirichlet series where the coefficients count something, they have a meaning, the sum of an over n to the s, where an is the count of something, then you can hope to prove what the value, special value is. So the sum of an over n to the s, when you have just the zeta function, is the number of ideals of norm n. That's a count. But in general, it's some twisted thing with characters. It's not counting a physical object, so that makes it more difficult. And he told me that's why the Birchland, Swinner, and Dyer conjecture is hard, because the ANs don't count anything. The APs count something, but the ANs don't count anything. Anyways, that's just some philosophy. But all right, when chi is quadratic, then we have a proof of the Stark's conjecture. Just by knowing two sides of this equation, we can then solve for the third element of it. So when it's quadratic, you have the simple factorization. You always have factorization, but there's multiple terms here if chi is not quadratic. So when chi is quadratic, then you know all about the thing you're interested in. And then I can say that the R chi equals 0 case is, that's just saying the value is algebraic in that case, and that's the Siegel-Klingen theorem. And I should also say that Shintani has a proof, a separate proof of that. Okay. So now let's move to the p-adic conjectures. So as I mentioned, the order of vanishing, a lower bound is actually known. The order of vanishing at s equals 0 is greater than or equal to r psi. Okay, so this follows from Weil's proof of the main conjecture, and then both Spiess and me together with Charles, we proved it directly analytically. That is, we just studied the p-adic L function and calculated the first r psi minus 1 derivatives and proved that it's equal to 0. There's no algebraic counterpart that we pass to via the Iwasawa main conjecture. It's just a study of the p-adic L function. So these are kind of very recent proofs that are alternative to this.
Even with Weil's, it's not obvious on the algebraic side that there are R zeros for algebraic.
Yeah, it's not obvious, I guess, but it's something you can do.
It's known.
Yeah, it's known. So. And in fact, in Weil's original work, there are some assumptions that actually even later had to be removed. But it is fully known using Weil's method now that you can do this. But anyways, we have a separate proof that's purely analytic. Again, the R0 makes some trivial comments. That the R0 R psi equals 0 case is trivial by the interpolation property. And okay, so then also recent work a few years ago with Darmon and Pollack, we proved the R psi equals 1 case under some conditions that I won't state here. Okay, so this was going back to the method of the proof of the Iwasawa main conjecture, so Ribot's method. That was the technique that was used, combined with some ideas of Greenberg and Stevens that I'll discuss later. Okay, maybe I'll just say that the fact that even if you were to prove that the r psi derivative of this p-adic L function at 0 was equal to the p-adic regulator, right, as that's part of Gross's conjecture, I think the hardest part would actually be proving that regulator is not 0, and therefore this order of vanishing is equal to r psi. So somehow, the leading term is probably even harder than going from here to equality. Yeah, okay. And then the conjecture at s equals 1, I'll just say it's known when chi equals 1 due to Colmez, but I should be careful about what I'm saying it's known. What's known is that if you multiply by s minus 1 times the p-adic zeta function and take the limit as s goes to 1, then you get the p-adic regulator, okay, of the unit group of f. But the fact that that's non-zero is not known and in fact equivalent to Leopold's conjecture, as we've seen elsewhere in this conference. So it's not known that there is a pole in general for a totally real number field of the p-adic zeta function. Okay. And as I was writing the slide, it came to me that probably via factorization you could probably do it something for a quadratic character like this result of Sands but I haven't thought about that. It might be written down somewhere. I'm not sure. Just something to think about. Okay, so let me put everything together. So there's no formulas here, just in one slide. So again, for an odd character, we have it's a critical value. It's just given by a Bernoulli number. And the p-adic side, if psi of p is 1, then we have a trivial 0, and you have the Gross-Koblitz formula. At s equals 1, for an Archimedean, we have Dirichlet's theorem. This is all over Q. And for an even character, then we have Leopold's theorem on the p-adic side. For general f, there is Stark's conjecture, but we don't have this theory of p-adic L functions for arbitrary f and chi, so let me not say anything there. But then if we move to the case where f is totally real, then we do have the p-adic L functions. So at s equals 1, then you have the Sayre-Stark conjecture generalizing Stark's conjecture. And at s equals 0, you have the Gross-Stark conjecture, this trivial 0 conjecture. All right. So now I want to move on to elliptic curves and talk about the trivial 0 conjecture of Maser-Tate and Teitelbaum that was proven by Greenberg and Stevens. So for this, we take the setting of an elliptic curve over Q with conductor n. So its L series, I'll write as sum of an over n to the s, which has this Euler product formula, where AP is p plus 1 minus the number of points on E over FP. That is, to take the reduction of E mod P, then AP is defined by that formula. Okay, so again, I haven't defined the term critical value, but basically these are the types of things you can interpolate to make p-adic L functions, so that's why I care about it in this slide. And when you have a critical value, expect that you divide out by the appropriate period, you get a rational number. Okay, so that's known here. Okay, now saying that, there's actually a very precise formula for what this is supposed to be. The rank 0 case of the Birch-Swinner-Dyer formula says that if E of Q is finite, then this should be equal to something in terms of the Tamagawa numbers of E, the size of Shah of E, and the size of the torsion of the Mordell-Weil group of E. And if E of Q is not finite, this is supposed to be 0. And that's all very much open. Okay. Oops. I mean, I guess it's known that if this is non-zero, then E of Q is finite, but the other direction is not known. Okay. So now that I've said that it's a critical value and that if you divide out by the appropriate period that it's algebraic, you can hope to interpolate such things to make p-adic L function. Of course, I only told you one value. You can't interpolate one number and make a function out of it. So the idea is here you twist by p-power conductor Dirichlet characters. Okay. So in the case that we saw of the Kubota-Leopold p-adic L function or of the Deligne-Ribet p-adic L function, you had a whole slew of numbers you could plug in. You could plug in all non-positive integers. Those were all critical and numbers you could interpolate, and they were dense in ZP, and you could define a function this way. Here, to get an infinite collection of values, you need to introduce twisting by these characters, because the only number that we're looking at is at 1, the only value of s. Okay, so I haven't said here how you interpolate these twists and make a function on ZP. Okay, but I'll talk about that in my next talk. But needless to say, I just want to have the idea that there is a p-adic L function and it's defined by these special values. Okay. So now, there's also a case in which there's a trivial 0 phenomenon of this p-adic L function, so that's what I want to talk about. So the interpolation property that I didn't write down precisely, but there is one that relates the value of LP of E at 1, so in general twisted by a character, to the value of this classical thing twisted by a character. And when the character is trivial, the interpolation property is very simple actually. There's this simple thing that looks like an Euler factor. It's 1 minus 1 over alpha p squared. So alpha p, again, I'll define in my next talk, but in the case that we care about, I can say exactly what it is. If E has split multiplicative reduction at p, that means that E has bad reduction at p, and that the set of non-singular points of E over Fp is isomorphic to Fp star, then we say that E has split multiplicative reduction at p. And in that case, it turns out that p fully divides this conductor, and the alpha p, which is equal to just the AP in this case.
This split multiplicative case, interpolation property is different from this, it seems to me. So this is for good primes. this interpolation property? No.
No, I mean this interpolation property is the correct interpolation property when P divides the conductor.
Oh, okay.
Yeah. Okay. So there's this 1 minus. Yeah. Okay. Yeah. Okay. So the multiplier above in this case it vanishes. It's 1 minus 1. Okay. So it's 0. So you have a trivial 0 here. Okay. So Mazur, Tate, and Teitelbaum considered what is the value of the derivative. Okay. I should mention that there is some notational issue. I mean, some people write, for some reason that I don't quite understand, there's a shift of s by s plus 1. Some people write this for the value of LP of E at 0, which may cause some confusion. So someone would say the derivative of LP of E at 0. But this is more, makes more sense to me because you're interpolating the value at 1. Let's call it the value of the p-adic L function at 1. Okay, so what was their conjecture, Mazur, Tate, and Teitelbaum? So first of all, if the classical L function is 0, they conjecture that the derivative is 0. And if the classical value is non-zero, then they said, well, it's natural to consider the ratio of the leading term, or the derivative, I should say, of the p-adic L function of E at 1 with the value of the algebraic part of the classical L function at 1. And say, what is that equal to? Okay. And so the conjecture was that it's equal to the same kind of expression that we saw before when I was talking about the Gross-Koblitz formula, log p over org p, log p over org p of a number. So in this case, we don't have a unit, a p unit, like we did there. We have the Tate period of E. So when E has split multiplicative reduction, or multiplicative reduction in any case, Tate has a uniformization theorem of what the complex points of E of Cp look like, and it's Cp star modulo the powers of some number that's usually called the Tate period. So if you take this log q over org q, that's what we call the p-adic L invariant of E. Okay, so I'm going to call this the analytic L invariant because it's given by the derivative of this analytic function, the p-adic L function. I'm going to call this the p-adic L invariant just given by the p-adic uniformization of E. And the conjecture is that they are equal because they found that computationally. In fact, it's funny, Mazur told me that Teitelbaum was a student at Harvard at the time, and he was doing this, Mazur and Tate were doing these computations with Teitelbaum's help. I guess Teitelbaum was coding everything, and they were sitting around talking, well, if I take the classical thing and divide out by the classical period, then, I mean, what do we get if we take the p-adic thing? And then Teitelbaum said, well, maybe it's the p-adic period. And Mazur and Tate said, that's way too simple of an idea because the p-adic L function is just made by interpolating these classical L values. It doesn't know anything about the p-adic uniformization of E. It's not defined using the p-adic geometry of E in any way. It's defined using classical L values, which you can interpret in terms of modular symbols on the upper half plane. There's nothing p-adic about that. How in the world is that going to know about the p-adic period? But then, Teitelbaum, being a fearless graduate student, went back and did computations and showed them that to several p-adic digits he was getting the p-adic period, and that's how they were able to formulate the conjecture. Okay, so this was proven by Greenberg and Stevens. So I just want to mention some aspects of this proof, as it will come up in my last talk on Friday. So the first is that Greenberg and Stevens gave an interpretation of the p-adic L invariant in terms of Galois homology. So if we consider the Tate module of your elliptic curve, which we've seen in several talks, then that is a module for the Galois group. Okay, so you get a homomorphism from GQ, the Galois group of Q, into GL2 of ZP just by choosing an arbitrary basis of this. And the Tate uniformization, that's just the statement that E of Cp is isomorphic to Cp star mod Q to the Z, implies that we know what this Galois representation looks like if we restrict to a decomposition group at P, meaning the Galois group of QP bar over QP. Okay, we know that so this is given by the Tate module. We know that what the p to the n torsion are given by here. They're given by the p to the nth roots of Q and the p to the nth roots of unity. So you look at how Galois acts on that. So the p to the nth roots of unity give you this cyclotomic character. P to the nth roots of q give you sort of 1 with an extension class given by kappa. So kappa, just from the fact that this is a homomorphism, you can see it lies in H1 of GQP of ZP of 1, exact same homology group that we've seen occurring in greater generality in Sharifi's talks. Okay, so this sort of H1 classifies extensions, and that's what this kappa is. It's an extension of 1 by cyclotomic character. Okay, so I just repeated that here. So it turns out this H1 is two-dimensional and has a certain canonical basis, which you might call kappa ord and kappa log. And the slope of your kappa that arises from this Galois representation is defined to be the algebraic L invariant of E. And what Greenberg and Stevens proved that the p-adic L invariant is equal to the algebraic L invariant. And this is actually quite simple. It's almost a definition if you take the right basis. Then it turns out that somehow this kappa log is defined by p-adic unit, and this kappa ord is defined by p, and somehow the ratio between, that's why they're called log and ord, the ratio between the coordinate with respect to the log and the coordinate with respect to the ord is exactly the log of a number divided by the ord of the number. This is almost the definition. So this is not a very fancy thing here. I mean, the only fancy part, well, okay, let me just, yeah, I would say the only fancy part of it is this isomorphism, which basically boils down to Tate duality. So, okay, so the next step is that they want to make an intermediary. So they have this analytic L invariant that they want to prove is equal to a p-adic L invariant. And I said that the p-adic L invariant is equal to an algebraic L invariant. So there's still something very deep that's missing. That's the connection between the algebraic and the analytic. That's usually the hard part of special value formula in the first place, is connecting the analytic and the algebraic. And the link that they found between the two is given by the theory of Hita families. Okay? So I want to give a very approximate definition of a Hita family in this talk. This is not the formal and correct definition, but it's a working definition that I'll use in my talks today and on Friday, which is that a Hita family is a formal Q expansion where the Fourier coefficients are p-adic analytic functions. Okay, where each of these ANs is a p-adic analytic function with the property, the remarkable property, that if you plug in an integer into these functions, an integer greater than or equal to 2, then in fact these numbers are algebraic. So then I have a sum of some algebraic numbers times q to the n, which I could think of these algebraic numbers as complex numbers. So then I have an honest Q series valued in coefficients and complex numbers, and I can ask for that to be the Q expansion of a modular form. Okay, and if it's a p-ordinary classical modular form that's an eigenform of weight k, right, so that's how the k variable affects it, then it's called a Hita family. So this theory of Hita families was generalized by Coleman, who removed this p-ordinary condition on the theory in Hita's theory. Okay, so that's the definition of a Hita family. And so using these Hita families, Greenberg and Stevens were able to find the link between the algebraic and the analytic. So that link I'll call the Greenberg-Stevens L invariant, which is, you can prove, and that Hita did this, Hita proved that there is a Hita family that specializes in weight 2 to the modular form associated to your elliptic curve E. Okay, so the modular form associated to E is just the sum of an q to the n. These are the same ans that showed up in the L series. So what Hita proved is that there are p-adic analytic functions that specialize so that an of 2 is equal to this an, and they have the further property that at the other positive integers k, you're getting the Q expansion of a form of weight k. And what Greenberg and Stevens realized is that the important thing is the derivative of the pth Fourier coefficient of this family at the point that you're interested in, at 2. So when you specialize to 2, AP of 2 would just be AP, which in the case of our assumption would just be 1. With split multiplicative reduction, that's just 1. So AP of 2 is just once, but the derivative there is somehow encoding these L invariants up to this factor of -2. Okay? So that's what they proved. They proved that both the analytic and the algebraic L invariants were equal to this middle L invariant that I defined, which I called the Greenberg-Stevens L invariant. Okay, and this completed proving this equality along with the previous equality that I explained, proved the Maser-Tate-Teitelbaum conjecture. So let me just explain briefly in one sentence the steps, which are very intricate and very, very clever arguments. So this was a purely analytic argument using the Mazer-Kitagawa two-variable p-adic L function. Okay, so the p-adic L function of E, which is just LP of ES, interpolates into a two-variable function where you also variable the weight. So when k is equal to 2, this is just LP of ES. If you fix k equals 2, you get a function of one variable s that's just LP of ES. It interpolates, it's just one fiber of a two-variable function, p-adic L function. Then they proved that the Greenberg-Stevens L invariant is equal to the algebraic, and they did that by using the theory of Hida and Wiles of p-ordinary representations. Okay, so the UP eigenvalue of your Hida family shows up in the representation, and that's the analytic function AP. So that's how that's related to the algebraic L invariant. So this Greenberg-Stevens L invariant is the link between the algebraic and the analytic. And I already explained that this last thing is elementary. Okay, so summarizing what I just explained, so this is the second to last slide, that if you have a critical, S equals 1 is a critical value, so this ratio is always a rational number, and under a certain assumption you can force it to be 0 trivially by the interpolation property. Okay, and Greenberg and Stevens then proved, so ignoring the p-adic L invariant for a moment, and just thinking about the algebraic and analytic, those are the things that generalize to other contexts. They prove that they're equal, and that's what I want to discuss another example of next time I talk on Friday. So the analytic being the main important part of it being the derivative of the p-adic L function, and the algebraic being an invariant of a Galois homology class. Remember, it was the slope with respect to a certain basis of this space, which is isomorphic to ZP squared. Okay, so now for my last slide, I just want to give a preview of my talk on Friday, which is the next case that you would think of a trivial zero, is if you have any elliptic curve over Q, and you don't need to assume that it has a multiplicative reduction at P. Instead of fact, assume it has good reduction at P. That's fine. The p-adic L function associated to the symmetric square of E always has a trivial zero at S equals 1. Okay? So you can define an analytic L invariant just to be so there's a trivial zero, so you ask for the derivative. So you ask for the derivative, and just as in the other case, you divide out by this algebraic number, which is the algebraic part of the classical value at 1. And then similarly, on the algebraic side, there's an invariant of a cohomology class. Again, the local cohomology class, if you impose the right conditions, is two-dimensional, and your global thing spans a line, and it's the slope of that line is the algebraic class. And Greenberg conjectured that these two are equal. Okay, so this is the very next case. So there are basically no other known cases of trivial zero conjecture other than the ones that I've described in my talk today. And so the very next case is this case, and that's what I want to discuss on Friday. Okay, thanks very much.